Okay, so now let's make a bit of a deviation from the chemistry subject itself and talk about science in general, and more specifically, let's talk about the scientific method, which is basically the method that is used by scientists to determine or explain what we observe in nature. Now, the first thing you need to recognize is that scientific knowledge must be testable, reproducible, explanatory, predictive, and tentative. These are all important, right? Especially when it comes to, well, they're all important. I can't even say which one is more important. But let me just highlight reproducibility. That's very important because whenever a scientist does an experiment, then another scientist should be able to follow the same procedure that the first scientist followed, and end up with generally the same results, all right? And this is basically what is done when it comes to the practice of good science. So the method that is used, of course, as I said before, is a scientific method. And the first step in this process is basically to construct a hypothesis. In fact, the first step actually is the observation, basically a statement of what is seen or known that is observed in nature concerning a particular phenomena. And then after that, you construct an observation, which, as you can see on the screen, is a tentative explanation, and I should probably add a reasonable tentative explanation of what is observed, all right? Then, and this is probably where the job of a scientist is most challenging, the scientist would have to basically design and perform an experiment for the explicit purpose of testing the hypothesis. So basically, you're testing to see if the hypothesis is falsifiable. You're designing an experiment basically to knock down the hypothesis. If the hypothesis is able to stand up to the testing, then basically the hypothesis remains. But of course, if you design an experiment which gives a result which is not predicted by the hypothesis, then what you'd have to do is basically change the hypothesis. But we'll get to that later on. In any case, at this stage, what you'll be doing is collecting data, which of course involves the taking of measurements, which we'll talk about in more detail shortly. So, as I said before, the hypothesis is tested. More than likely, especially at the initial stages, you would have to revise the hypothesis so that it fits the data that is obtained by the experiment. And this process is continuous. In other words, you end up with a new hypothesis, which is further tested, and then it is further refined, and then you end up with a new hypothesis after that, which is further tested, and so on and so forth. So after you have successive testing and refinement of the hypothesis, when you end up with a situation where the hypothesis is able to successfully predict what will happen, then we designate it as a scientific law. Usually, not in all cases, but usually the law can be expressed as a mathematical equation. An example of this, which you're going to meet later on in chapter 5, is Boyle's law, which basically is a description of the relationship between the pressure of a gas and its volume. And there's a mathematical equation which says basically that the pressure is inversely proportional to the volume, and that law was arrived at as a result of repeated testing of experiments conducted by Robert Boyle, and that led to his law, which is known as Boyle's law. Now, a very important aspect of the scientific method is the development of what is known as a theory. Now, a theory is different from the hypothesis. If you recall, we said that the hypothesis is basically a reasonable explanation of what is observed, but it's not tested, right? It's after the testing, the repeated testing, and the repeated changes made to the hypothesis as a result of the repeating testing, then you end up with a situation where there's harmony between the data and the hypothesis. Then that hypothesis ends up now being called the theory. So the theory is basically an explanation. The explanation which explains basically what is observed in the law. And the example I gave you earlier is Boyle's law, which says that the pressure times the volume for a gas is constant at a constant temperature. And the theory that is used to explain that law is what is known as the kinetic molecular theory. We're going to get into this in chapter 5, but basically what this theory says, among other things, is that a gas exists at the particle level as high energy particles always moving, and therefore when you have the reduction of the volume, the particles are squeezed into a smaller volume, they will collide with the walls of the container with greater force and more frequency, and therefore that will be manifested as greater pressure exerted against the walls of the gas container. All right, so that's an example of a theory which explains what we observe in the law. All right, so this diagram here basically is a flowchart explaining the scientific method. As I said before, the first step is where you make your observations and then you come up with your reasonable explanation, which is your hypothesis, and then you test your hypothesis by designing and conducting experiments, which of course is designed in such a way so as to test the hypothesis. So this is where you might have, or not might, but you will have a situation where after experimentation, you have to revise your hypothesis, or in some cases, you might have to replace the hypothesis with a new hypothesis. That is known to occur. And this happens over and over again until you get harmony between the hypothesis and the experimental data. That leads us, of course, to the theory, which is basically the model that is used to explain what is observed. But the difference between the theory and the hypothesis is that the theory is backed by the data obtained from the experiment, while the hypothesis was arrived at simply by putting forward a reasonable explanation, and that serves the basis for testing by experimentation, which leads ultimately to your theory. Now, I would say this is probably the beautiful thing about the scientific method. The most remarkable thing about the scientific method is that when you end up with your theory, that does not necessarily mean that that's the end of the story, all right? Because you might have a situation, and this is actually known to happen in science. If you look at the history of science, you'll see that there are instances where you might have a theory that has been accepted by the scientific community for even centuries, and then somebody out of the blue does some experiment, in some cases even by accident, end up with results which basically destroys the theory, and therefore, as a result, you have to basically ditch that theory and come up with a new one, all right? So that's why there's an additional step provided here where it says further experiment. That is known to happen. I could go into many stories where basically this happens, where a theory is accepted for a long time and then somebody comes up with an experiment which basically destroys that theory. So the point here I'm making is that science is an ever-evolving field, right? There are no sacred cows, right? Everything is based on the available information arising from experiments that were done at the particular time. No theory is safe, let's put it that way. Every theory that has been established, even those that have been established for a long time, is subject to scrutiny and testing, and potentially can be replaced by a better theory as long as there's enough evidence to support the better theory. Okay, so that's basically it as far as the scientific method is concerned. I'm going to stop here, and the next topic we'll discuss is scientific measurements.